Hey, y'all. Today we are going to start talking about one of maybe the most important things and something that will carry throughout the year, and that is the normal distribution. And so far we've talked about types of data, categorical, quantitative. We've described quantitative data, the distributions of those data sets. We've compared quantitative data sets, their shapes, their centers, their spreads, any unusual characteristics. And so now we're going to talk about one special distribution. Before we talk about that, we're going to talk about this thing called a z-score. And a z-score is really just a way to measure how many standard deviations we are away from the mean. I'm going to say SD. So sometimes we'll want to compare data sets that are not directly comparable. And so what we can do is we can standardize scores, or we can standardize data points from one data set and compare it to a standardized data point from another data set so that we can compare. And the way we compare them using z-scores is it'll tell us how far is this thing away from the mean? How far is this data point? How many standard deviations is this data point away from the mean? And this formula right here is how you're going to see this presented on the formula sheet. Because there are different standardized test statistics. That's what a z-score is. And so the way we are going to look at a z-score is going to say z is equal to, and our statistic is something we're getting from our data set. So our data point, so we're going to call it x. And our parameter is going to come from, excuse me, our population. In this case, we're talking about means. So mu. And standard error for us right now, we'll just call the standard deviation. So we have a z-score, a standardized score. We have our data point, x, our mean, and our standard deviation. And so if you pause here and you take a second, you read this, what we're going to do is just show an example of how we can compare the success from one class to success in another class, even if they're not directly related. So here we have somebody scoring an 82 on a French exam and an 86 on a math exam. And so we want to compare, which one is actually better. And so French and math are not directly comparable classes. So we can standardize these scores using our z-score formula. And so let me set that up. So here I've calculated the z-scores for both classes. My 82 is here for French. That is my actual data point, the actual French score. And then I have the mean of that exam and the standard deviation. And you calculate that out to get 1.25. 86 here is the score on the math exam. The mean is 68. Standard deviation is 12. When we simplify that right side, we get 1.5. And so you could say that the math score was higher, but we can't really compare a math score to a French score. But when we standardize them, when we find the Z's, we can compare them, and we can see that the Z-score for the math exam is higher. That means that the score on the math exam was 1.5 standard deviations above the average score. Whereas for the French exam, we are 1.25 standard deviations above the average score. And so this person did better compared to their peers on the math test. Not just looking at the raw score, but looking at the standardized Z value. And so you can calculate z-scores no matter what a distribution looks like, but what they really come into play a lot when we talk about the normal model. And so we have a symmetric distribution here. We would talk about the center being located at the mean. In this case, the mean is 0. 0 for a standard normal curve, but we can use values from our problems. We'll talk more about that. There shouldn't be any outliers here. Our standard deviation when we have a standard normal curve is 1. As you can see, we go out 1 standard deviation, 2, and 3 to both directions. And if we go 3 standard deviations in either direction from our mean in a approximately normal distribution, we will have almost all of our data points accounted for, 99.7% approximately. We would say that approximately 68% of all our data points would fall between 1 standard deviation of our mean. 95% approximately would fall between 2 standard deviations of our mean. And then almost all, like I said before, will fall within 3 standard deviations. The area underneath the curve represents the proportion of data points that exist in that space. So as you can see, 68%, that's the biggest chunk, and that's the biggest area underneath our curve here. We do have some notation when we want to talk about a normal model. In order to shorthand that, we use capital N, and then in parentheses, we note the models or the distribution's mean and standard deviation. And there's going to be variations of that as we go. But for now, if you read something that looks like this, that means we're talking about a normal model or normal distribution, something that is approximately symmetric with whatever value this is as the mean, and the second value would be the standard deviation. So pause here, take a minute, read this problem, and then we will discuss it. Okay, so I went ahead and I drew the model for this scenario. We can put the mean right in the middle. So this said we had a mean MPG of 24.8 when we talk about the fuel economy for automobiles. It has a standard deviation of 6.2. So in our normal model, we're going to go 3 standard deviations to the right above the mean, 3 standard deviations to the left below the mean. And literally what that means is I'm going to add 6.2 and then 6.2 and then 6.2. And then I'm going to subtract from my mean 6.2 and then 6.2 more and then 6.2 more. And that will give me 3 standard deviations above and below the mean. And so what that means is that 68% of my data, which is what part B asks for, should fall between 18.6 mpg and 31 mpg. So 68% of my automobiles approximately will have a miles per gallon between 18.6 and 31 based on our 68, 95, 99.7 rule. We also want to know here what percent of autos should get more than 31 miles per gallon. So 31 miles per gallon is 1 standard deviation away. This is a symmetric distribution. So if this middle chunk is 68%, then each of these other 2 areas are going to be equal, and they're going to have to make up the rest of the area. So there is 32% left over. That means there's 16% in each remaining area. So this area here above 31 miles per gallon is about 16% of our automobiles. It's important to note when we're looking at a normal distribution, something that's approximately normal, that anything above or below 2 standard deviations from the mean is unusual. So above or below 2 standard deviations would be an unusual value. So any car here that it has a gas mileage smaller than 12.4 or larger than 37.2, we're going to say that's an unusual gas mileage or fuel economy, we should say. Take a minute, read this one, and then we will talk about it. So here we're talking about the weight of steers. And it says we have a normal model with standard deviation 84, and we had a mean weight of 1,152 pounds. So here is our notation for that. And we're trying to find percentages. Well, percentages are areas underneath this normal curve. And so I always recommend that you sketch this out. And even if you just put the mean on here, we can get an idea of what we're looking for. So I want to know the percent of this model that is above 1,250. Well, 1,250 is going to be to the right of my mean. It doesn't matter where it is. And so I'm looking for this area underneath my curve. And so on our calculator, we have a way to calculate that area. We're going to hit the second button, and we're going to hit this vars key, the blue that says DISTR for distribution. And we're going to choose the second option. And we're basically going to tell the calculator what our picture looks like. So this value right here is 1,250. And this graph goes, or this distribution goes to the right infinitely. And so usually to represent that, I'm going to say it's 1e to the 99. Just a really, really big number. And so when it says lower, that means left. It's like, hey, where's the area on your curve? Where's the left? The left is at 1250. The upper side is that tail that goes on and on forever. So I'm going to say 1e. I got it finally. E to the 99. And then I'm going to tell the calculator what are my mean and standard deviation. And it's going to give me a decimal, which we can convert to a percentage if we want, which is 12.17. We can expect 12.17 approximately of these steer to have a weight over 1,250. If we wanted to do under 1,200, well, 1,200 again is going to be somewhere above the mean, but less than that. We want to say under. So we're looking for this area now to the left. And so on the left here, I'm going to have negative 1e to the 99. And on the right is going to be that 1,200. So I'm going to tell my calculator, I'm going to say second vars, choose the second option. I'm going to tell the calculator the left is 1e to the 99. It goes on forever. It's my left tail. The right part of my shading is 1,200. I have the same mean and standard deviation. And so I can find that approximately 71.61% is going to be, did I say 61? Yep. Is going to be less than or under 1,200 pounds. And then if we wanted to go between, it's the same idea. We're just going to put on here. So between 1,000 is somewhere over here. It doesn't have to be exact. These sketches are really just for us. 1,100 is still going to be to the left of my mean. We're looking for this area. And so I can tell my calculator, I want to calculate between 1,000 and 1,100 with the same mean and standard deviation. And I can find that to be 23.28%. The pictures really help here. They give you an idea of what's on the left, what's on the right. The calculator, when it says lower, it means left. When it says upper, it means right. We're just telling it, hey, here's my normal distribution. This is the mean and standard deviation. Please tell me what percentage of values would fall between these two numbers. We'll talk more about the normal model and z-scores and actually some more about the calculator in the next lesson. But for now, that's it. If you do have questions, please ask. Make sure you stick around and answer the questions associated with this lesson. If you need help, ask, and good luck.